Hi, we were discussing about model predictive control and its applications. We have covered, we have gone through until the history of MPC. Now we will come to the basic components of MPC. The basic components are the prediction, optimization, receding horizon implementation. Now, what is prediction? How are we predicting? We are using the dynamic model of the discrete time linear system xk plus 1 is equal to axk plus buk to predict the future states and the control of the system. Now, we are representing capital UK as a vector of future control inputs. So this notation is nothing but the control given at k instant, provided you have the state value of the kth instant. This is nothing but what is your predicted k plus first control input, provided you are at the kth instant. Similarly, until n, where n is the prediction horizon. Now xk is nothing but the predicted state at k plus first instant, provided you have the state at the kth instant. Similarly, xk plus 2 state at the k plus 2th instant, provided you have the state at the kth instant. Now the evaluation of state according to the prediction model will be like this. So you substitute I as a 0, 1, 2 up to n to get the state sequence. With the initial condition xk given k is equal to xk. We are representing xk as xk given k. That is the initial condition. So we are predicting using the model of the system. Now, what is optimization? We are minimizing a predicted performance cost. Normally, it will be a quadratic cost, and the general form of predicted cost is given here. So, where n is the prediction horizon. So, we will be taking the states until n terms and control sequence until n terms, and this is the final cost. So by this notation, what we are defining is we are taking the norm with the weight q. So x transpose qx, where q and r, here q and r are positive definite metrics. And by the optimization problem is nothing but we are trying to minimize this cost and find a control sequence. So that will be the optimal control sequence. We will be substituting the control inputs are the degrees of freedom. So we will be substituting different values and find a suitable optimal control value. So which minimizes this cost JK. Now, what is receding horizon implementation? Only the first element of the optimally predicted input sequence is implemented. So at this stage, we will have a control sequence and we will implement only one control sequence. And for the next instant, we will be again predicting for n instances. So this is the prediction horizon at the time k until this, and then at the next instant we will be again predicting for so many instances. So this horizon is receding, it is moving. So that is why MPC is also called as a receding horizon controller and moving horizon controller. So we repeat the optimization at each sampling instant. The prediction horizon has a fixed length. In the literature you can find other cases as well, but basically this prediction horizon is fixed in length. Now the models that we are using may be a linear model or a non-linear model. Based on this, there are different classifications for MPC, like linear MPC, non-linear MPC, and the model can also be discrete in nature, continuous in nature. Even though our implementation is discrete in nature, there are continuous type models used for MPC. Now we'll see constraints, different types of constraints. The main advantage of model predictive control is its capability to incorporate the constraints within the problem formulation. So every practical systems will have constraints. So it may be equality constraints or inequality constraints. It may be hard constraints or a soft constraints. Hard constraints are which cannot be violated. Say, for example, the valve opening from 0 to 100%. It cannot go beyond 100%. So those are hard constraints. Soft constraints are mostly state constraints that shows that even if it violates a little bit, we can tolerate that violation. So those are soft constraints. Input constraints are represented like this. This is the lower bound, this is the upper bound, and this is the control value. State constraints are represented like this with a lower bound, upper bound, and state. State should lie between these two. So based on this, whether we are using hard or soft constraints, again, the problem MPC will be divided into many different cases. We'll see that in later slides. Now we will begin with unconstrained optimization. The predicted state sequence are like this. The xk given k is nothing but the present state. Xk plus 1 given k is predicted by using our model axk plus buk. And xk plus 2 given k is nothing but it is a xk plus 1 plus buk plus 1. So you have the value of xk plus 1 from here. Substituting that, you will get a square xk plus abuk plus abuk plus 1 given k. So instead of xk plus 1, we are substituting this value here. So we will get a term like this. And similarly, when we are writing xk plus 3 given k, we will be writing this value instead of xk plus 2 in we will be writing this value and rearrange. So that can continue. So this is a compact notation of the future states. So xk plus I given k is nothing but a raised to I xk plus phi I uk. So I have written here what is phi I. It is the ith row of this matrix phi. So compact notation will be xk is equal to x. Sorry, it should have been xk plus 1, xk plus I. So xk plus I is equal to m xk plus phi uk. So you are writing every future states in terms of xk and uk. So m is nothing but all these terms and phi is nothing but these terms. So this is a compact notation of all the future states of predicted states of MPC using the model. Now, when we substitute xk plus I given k in the cost function, xk plus I given k, this term in the cost function, we can rearrange. We can write this cost function in terms of xk and uk alone. So the cost function mainly depends on two factors. One is present state and the control sequence. So this future states can also be written in terms of present state and control sequence. So that is what we are doing now. We are rearranging the whole term and writing it in terms of control sequence, present state. So only terms in this, only degrees of freedom in this term is control sequence and the present state. So you can do it, you can substitute and see, you can rearrange and see, you will get these terms. So H is nothing but this, F and G are given here. So this will be a matrix. Q bar is nothing but a matrix of Q values in diagonal. R bar is a matrix of R in diagonal. So after getting the after rearranging the cost in terms of UK and XK, you are taking the derivative with respect to U. So when you are taking derivative, what happens is this term will be there, this term will be there, this term, since we are taking derivative with respect to u, you can avoid this term. So from these two terms, after taking derivative, you will get 2hu plus 2fx. So at the optimal cost, the rate of change of cost will be 0. So when you can substitute it as 0. So 2hu plus 2fx is equal to 0. And from that, you can find the optimal control sequence. U star, it should have been capital U. U star is equal to minus H inverse F xk. So you are getting the optimal control sequence like this. And you are taking only this is the K value. And you are taking the only first control input. So that is why I have multiplied it with a matrix with taking only the first element. So that will be optimal u1 star. So that is how you find the optimal control input for the first instant. So we are trying that for a simple system. So as an example, I have given the matrix ABC. So after, what you have to do is you have to substitute and find the values of H, F, and G. Resubstitute in G is not required. Resubstitute in this and take only the first element. So you will get this as the first element. So when you simulate, you run the system, you will get the states as this, and you will get the control as this. So it is a regulating problem. You are regulating it to a 0 value. So this is an example of unconstrained optimization. We have not considered any constraints for the states as well as the control. So this is a simple unconstrained optimization. To begin with, we will start with an unconstrained optimization, and we will see how constraints are incorporated in the next lecture. So these are the few recommended readings of this book. This whole lecture is based on these books. So the main contribution of this lecture comes from this predictive control for linear and hybrid systems. And this is a simple, to understand it in a simple way, this will be very useful. Chapter 16 is on MPC from this book, and they have given few examples, and mainly they are discussing about generalized predictive control and dynamic matrix control. So those are the preliminary, while introducing MPC, they were the preliminary approaches. So you can just go through them, but this is the main text that we will be following. Now, to summarize, what we have seen is the basic MPC formulation, the concept of MPC, terminologies used in MPC framework, history of MPC, and unconstrained optimization. We discussed a problem on unconstrained optimization. So thank you.